Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shops. I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So today we are going it back to basics, and I'm surprised it took us this long to get to this point where we're talking about all these different tests and things we can do throughout these classes, and we really haven't discussed the general basics of electronics and electrical testing. What is a volt? What is current? How do they relate to each other? How do I test these different things like dwell and different time bases and things like that? So we're going to walk through all of these basic type questions tonight and hopefully get you a little bit better understanding of how electricity works. So thinking of electricity, that's where it all starts. We're testing electricity most times when it comes to testing components on a vehicle. So electricity is, of course, a form of energy. It's not the only form of energy. We have kinetic energy and heat energy and light energy and multiple other forms of energy out there. So electricity can either be stored or converted to another form of energy. So we can take that electricity and turn it into light, or we can turn it into heat, or we can turn it into motion, kinetic energy. Now, electricity travels through a conductor. So think about maybe the copper wires under the vehicle is probably the most likely way we're going to experience that on a car. So through a conductor. Does not travel easily through an insulator. So if we think about the outside of an electrical wire, an electrical harness, is usually plastic or rubberized something, and doesn't travel easily through that. So that's why we call it an insulator. It keeps that electricity in. And also, since it is a form of energy, we can measure the properties of the energy, as it were. So we'll talk about the different properties we'll be running into as we go through this course here. So first off, it's going to be voltage. So AC voltage is one way that we see this. Now, it is a type of electricity, which stands for alternating current. So the voltage switches from positive to negative polarity. And if you were to watch it on a scope screen, it kind of goes up and down like a wave, back and forth. We can see AC voltage generated by some vehicle components, like speed sensors. If you think about an analog speed sensor, wheel speed sensor, you see it go up and down. Some cam and crank sensors will be an AC type signal generator. They'll have a positive and a negative, and they'll send a signal out on opposite sides of zero. Pickup coils can work in much the same way. And then magnetic fields also generate an AC voltage. If we think about an alternator, what's an alternator? Really just generates a magnetic field, and then that generates an AC voltage, which then through the electronics in the back of the alternator, the rectifiers and so on, turns it into DC voltage, and then it's being able to use for the vehicle. Also, if we think about hybrid and electric vehicles that are becoming way more common on the road now, those electric motors in those vehicles usually use three-phase AC. So we do run into it from time to time on a vehicle, and it seems like it's going to be a lot more prevalent as we go into these hybrid and electric cars in the future. Then we get to DC voltage. So that's the most common one you'd probably be most familiar with if you've done any automotive testing, because that's generally what's used on a vehicle. So it stands for direct current. In this case, it doesn't switch polarity, the back and forth. It's just a direct voltage from a stored source, like a battery. Now, in this case, the measurements are also taken in parallel with the circuit, so we wouldn't want to break the circuit apart and take separate measurements that way. It's really like back probing a wire, something of that nature is going to be, so as we said, in parallel with the circuit. And as I said, it is the most common type of voltage in automotive systems. So battery voltage, charging voltage, 14 volts, what have you. 5-volt reference voltage is very common on vehicles, ignition voltage, and so on. So a lot of different DC voltages we're going to see on a vehicle. Now let's talk about how we're going to measure that. And voltage is one way, but we have voltage, amperage, and ohms or resistance. Now these are really the three ways. Remember how I said we can measure energy, and they're all interrelated through this law we have called Ohm's Law. So Ohm's Law states that voltage, amperage, and resistance are all directly proportional to each other. So if we use this triangle here on the bottom right-hand side, we can see where everybody falls. So E stands for volts, I stands for current or amperage, and then R stands for resistance or ohms. So if we know at least two of these things, we can figure out the other one. So for example, an oxygen sensor heater is supplied with 12 volts, and we know that oxygen sensor has a resistance of 4 ohms. How many amps is it going to draw? So the equation is, in this case, I, because we're looking for I, that would be the current, equals E over R. So E divided by R, so I have 12 volts and 4 ohms, so that gives me 3 amps. Now, if we wanted to work in the other way, what if I knew how many amps was in the circuit and how many ohms of resistance were in the circuit? I wanted to find out the voltage. Well, 3 times 4 equals 12. Or 12 divided by 3 equals 4. So they're all directly proportional to each other. As long as I know two of the parts of the triangle, I can find out the other third part. So that can help us when we're going through and trying to diagnose, how much current flow should I have? How is this resistance affecting my voltage and my current, and so on. So it is useful for seeing how they interrelate to each other. So at the top of the pyramid is voltage. So it is electromotive force or potential difference expressed in volts. So as we saw before, voltage can also be AC or DC. And I like to think of an analogy that a lot of people use when we're trying to discuss voltage, amperage, and resistance. Voltage is a measure of the pressure that allows electrons to flow. So we're thinking of, say, a water pipe or a river. What is the pressure of that electricity that's allowing the electrons to flow? So that's the voltage, is the measure of the pressure. Then we get to amperage or current. So amperage is the strength of an electric current expressed in amperes. So amperes, amperage. Amperage is a measure of the flow rate of electrons. So how are they flowing through this pipe or down this river? For automotive, amps measure the amount of effort it takes for a component to do something, like a switch to turn on, a motor to bring a window up and down, something like that, or the amount of current being drawn through the circuit as a whole. So I have multiple loads on a circuit, how much current is being drawn through to power those loads. Amperage flowing through a wire through a circuit creates a magnetic field as well, which allows us to measure it. High amperage can lead to heat. So if we think about how we diagnose a problem with high current flowing through a wiring harness, well, in that case, you might want to use thermal imaging, since it does generate a heat signature. I can see, well, in this spot, there is a problem and there's too much current. Can also be measured in line or inductively. So in line would be I break the circuit apart and I put my ammeter in between. So that's the old way we used to do it with the Vantage and the Vantage Pro. If you remember those two tools, they had a 10 amp fuse in there. So as long as it didn't draw over 10 amps through the circuit, you could use that in order to test it. Now the more preferred way of doing it, since we don't have to disconnect things, is going to be inductively using a low amp probe, current probe, whatever you want to call it. That is measuring the magnetic field. Since the current generates a magnetic field, the low amp probe can measure that magnetic field, turns it into a voltage, then gets read by the tool, and we're all good at that point. We're able to read it. Then we have resistance. So resistance is a measure of electrical restriction or a load that a component applies to a circuit. The primary unit of measurement for this is the ohm. Automotive components have specified resistance values. Now, the manufacturers might not always publish what their resistance is supposed to be, but oftentimes they do. So let's say it's a fuel injector and we need to see 14 ohms. So you would measure the resistance through the wiring inside that injector and read 14 ohms, you're good. If it's too high, it's not going to work well. If it's too low, it's not going to work well. So within that specified resistance, we'll supply the set amount of current that we need. Now the meter measures resistance by sending a fixed amount of voltage through a circuit. So if I'm measuring I'm measuring resistance in a circuit, what it's going to do is the meter itself will put, let's say, a volt. Depends on the meter, but let's just say for argument's sake or for this discussion that we're sending a volt through. Resistance is going to be determined by the amount of amperage needed to push that voltage through the circuit. So if I am pushing 1 volt through and I need 2 amps to put it through, this is how much resistance I'm going to have. So it must be measured in an open circuit with no voltage applied. If there's voltage applied, then we're not going to be able to test the resistance correctly with that. There's another test that we can do for that. So it must be measured on an open circuit with no voltage. So usually, for example, back to that fuel injector I just mentioned. Usually if we're going to test resistance on a fuel injector, they'll tell you to disconnect it and then test it at the injector itself to see what the resistance is through that circuit. So now let's talk about circuits and the different circuit types that we're going to run into. So a circuit in its most basic form. Now, if we look at a wiring diagram on a modern vehicle, it is definitely not this basic, but at its most basic and essential form, I'm going to have my electricity in DC, flow from a battery from the positive, goes through a load, whatever it happens to be, in this case, a light bulb, and then back to the negative, and then so on and so forth. It just makes a complete lap or circuit around this, this connector here and these wires here. So the simplest type of circuit is going to be a series circuit. So you see we have a ground here, we have a ground there, so that's common. That they'll be tied together through the ground point. Voltage comes out, powers up my component, and then we have a connection to ground, makes a completed circuit all the way around. So if you can imagine the ground here is tying these two together. That's why if I have a bad ground connector, it's not going to tie the two together. So we want to make sure that we have good power, good ground connectors. Now, if I have a problem in a series wiring circuit, if I have a problem on the power supply side, it's not going to work. Electricity can't get through there. I have a problem on the other side, still won't work because the energy will get to the bulb and then it won't be able to make it back to ground, so it won't have a completed circuit. So it'll stop flow of the electricity. So series circuits are pretty easy to, well, I can't say necessarily pretty easy, but it's a lot simpler to figure out than some other circuit types because it's somewhere in between point A and point B we have a problem. So it makes it a little bit simpler. Now, what about parallel circuits? Parallel circuits is where it gets a little bit more complicated. So we still have our ground, over here. We'll see that we have 3 circuits in this case. They're all parallel to each other, and they have a common power and a common ground. All of my bulbs are lit up because everything is good with the circuit. Now, if I put a break in the circuit, my circuit break is here, nobody works because the power isn't able to get through. What if I move my break over to here? Well, this light bulb will work because the circuit makes a complete circuit, but it doesn't get past this. So these two don't get fed. So we can still have a good circuit on this one. Well, what about if I moved it to here? So now my power still flows through these 2 circuits, but it's cut off there. So you need to get really good at reading wiring diagrams. Let's put it that way. Let's get really good at reading wiring diagrams and seeing how is this set up. Is it a series? Is it a parallel? Is it a series parallel, which we're going to see here in a second? How is it set up? And then what is wrong? What's not working? So in the case of this light bulb situation, if this bulb works and this bulb works, and I've already checked the bulb itself to make sure it's working, and I'm getting no voltage flowing through this circuit, then I know it's a problem somewhere past this break in the line right here. Because it's able to flow through here, it's able to flow through here, not able to flow through there. So it could be there or it could be there. We just want to measure and check in the circuit wherever the problem might be. So we need to be able to figure out where in the break, where is the break in the circuit. And then we have series parallel, which is a combination of the two. So in this case, we have a series circuit up until it breaks away and turns into a parallel. So you see I have the light bulb up top, the light bulb's down bottom. If I have a break at the beginning in the series part, Nobody gets electricity, nobody works. If I move it over to here, still nobody works because nothing can get down to ground. The power is not making it to any of the bulbs, and this bulb isn't, the electricity isn't making it down to ground. So we have a problem that'll still cause an issue in the circuit. What if I have my break over here? Well, this one's going to work because we have electricity flowing through there. We got it flowing through there. We got it flowing through there. So somewhere in that circuit, we have a problem. So it's just kind of understanding how the circuit's laid out and where do I need to test that circuit in order to figure that out. All right, so testing vehicle electronics. Now that we have some sort of a foundation here, what we're talking about, let's test some vehicle components, or at least talk about testing components. So before I begin, I want to understand this a little bit. So what's the operating voltage of this circuit? Is it an AC circuit? Is it a DC circuit? Because that'll depend on how I test it. 5-volt circuit, 12-volt circuit, what is it? What kind of circuit is it? Is it series? Is it parallel? Is it series parallel? What type of component do I have? Do I have access to the information that I need? Got to make sure you have access to all the information, because we know nowadays with a complex vehicle, information is going to be key when it comes to fixing vehicles. So here's an example wiring diagram, right? Do I have access to wiring diagram? Here is a split, and we'll look at this in a little more detail when we go live on the tool. But this is a 5-volt reference circuit on a Ford Explorer, and we see a couple of these sensors share the same power feed. So if my problem was over here, nothing past that break is going to work. So if that one doesn't work, that one doesn't work, that one doesn't work. I know my problem is before that. If my break is here, if we're looking for an open anyway, so if my break is here, then this sensor will still work, and this sensor will still have 5 volts, but this one won't. What if I had an internal problem? I remember there was a case study we did where a vehicle had a bad differential pressure feedback EGR sensor, DPFE sensor. It was shorted to ground, so it was pulling that 5-volt circuit down to half a volt for all of the components on that circuit. So if we're looking for a short, that's a different case. So in this case, it's shorted to ground. It's pulling it out of anything attached to it at that point. So if we're looking for an open, it's one way. If we're looking for a short, it's another way. We're also looking to see what kind of circuit is it. Do I have any splices in there, etc. So we want to be able to have a good knowledge of how that circuit's working. Also, we would want testing info for that particular component. Now, manufacturers oftentimes test it as part of their flow charts and such. But if you have a snap-on tool with a scope in it, it's going to also have the guided component database in there. We're just going to have all of my information in there. And the other nice thing about it, I actually saw somebody had a question on this on a Facebook forum post this week, was, well, I'm using guided component test, but I want to use my scope. Well, in guided component test, you are using your scope or the meter or the graphing meter. The nice thing about guided component test is I don't need to know anything about this component really. I just need to know where to hook it up. I probably want to know voltage and things like that, but I don't need to know. I need to set my time base to this, and I need to set my voltage to this. I don't need to worry about what meter to use because the tool will do all that for me. Now you can go in and manually change it as well, but I was just that was just kind of timely how that came up in a forum post I saw this week. So in this case, they're looking at a crank signal. So crank signal return, crank signal voltage positive and negative. So in that case, it looks like it's probably going to be an analog type of a sensor there, AC type sensor. So we can check that, and it gives us all the operation over there. It gives me my component connector over there. What types of components are we going to deal with? Well, it could be a signal generator of some kind, like the one we just saw. It could be a voltage generator. It could be a frequency generator. Some sensors work and transmit a frequency. Magnetic field generator. This could be a solenoid, a switch, a relay, a thermistor, motors, actuators, and more. By far, not an exhaustive list, but that's probably the majority of the ones you're going to find on a vehicle component now. Also, we need to understand, how do we know a circuit can carry a load? This one's kind of an interesting little story. So let's take and use an ohm meter to check a ground or check a circuit. Ohm meter to check a circuit, remember we said, has to have no voltage for it. Well, let's say we take a starter wire. Big fat starter wire, 130 strand copper. If I put an ohm meter on either side of that wire, what's my reading going to be? Assuming that there's nothing wrong with it. Assuming there's nothing wrong with it, you would say, I think you'd agree that we should see 0 ohms or very, very close to 0 ohms because we have a continuous, no worries, no resistance, no problem with the wire. So 0 ohms. Now let's take that big fat cable. Take one of those tiny little copper strands out of it and then put our ohm meter on either side. Just that one little tiny strand of copper wire. What do you think the reading is going to be? Well, it's going to be the same, right? Because we're passing a voltage through, and if I have no resistance, then it's not going to show anything there. But will this thin, tiny strand carry a load? Do you think I'll be able to start a car with that tiny strand of wire? Most likely not. It's going to get really hot, I think, if you try. So if I have a frayed harness, if I have a mouse that ate the harness, that happens. If I have a harness that rubbed on the back of the block or the cylinder head, and I have some sort of a frayed situation where there's only a couple pieces of copper still holding it together, if I use an ohm meter on that, it's still going to get a good circuit, according to the test. It's going to be 0 ohms. I have no resistance. I don't have a problem. But I can't carry any current through it because it's a high resistance. It's actually resistance to current. Since an ohm meter doesn't really load a circuit, we need to load the circuit. So another common technique that a lot of folks will use is they'll take a halogen headlight. I want to say analog headlight, but not an LED, a normal incandescent headlight or halogen headlight where it actually needs current to flow through it in order to light up. So if I hook it up and I'm checking both sides and it's dim, then I know I have a problem in the wiring somewhere. If it's nice and bright, then I know my wiring is continuous and I shouldn't have an issue that looks like that. So we want to make sure we're not just relying on ohm meters when we're checking for opens in a circuit, because it could be holding on by that little tiny bit and that can give you trouble. And that kind of leads me to this voltage drop. So voltage drop is a way of checking resistance in a circuit. So poor or corroded connections may cause unwanted or excessive resistance in a circuit. Now, of course, that can affect the accuracy of sensor inputs and outputs. And excessive circuit resistance can also cause circuit components to operate poorly or not at all. If I have too much resistance, I have very little voltage, just not going to work. Circuit resistance causes circuit voltage to drop below normal, anywhere really past that. So the circuit resistance before or after an electrical load can cause electrical system problems. Measuring the voltage drop across a circuit is the method of checking circuit resistance. Connect the tool across a suspected area. So the circuit must be live in this case. Remember, on the ohms, it was open. On this case, it wants to be live with voltage going through and the component or the load energized for the voltage drop to be measured. So in this case, we're measuring between here and here. It's before the problem. I'm not seeing much of a voltage drop at all. I'm seeing like 0.01 of a voltage drop. Now, if I take this and put it on the other side, though, so my positive's at the battery, my negative's in the wiring. If I move it on the other side, though, then my voltage drop increases because I have an increased resistance right there, and I can measure the voltage difference, the voltage drop between there. So maximum known good rule of thumb voltage drop. For a high current positive side, nowhere more than like 200 to 500 millivolts of a voltage drop. High current negative side, 100 millivolts. PCM circuits, 50 millivolts for a light gauge, and a low current circuit, 90 to 100 millivolts. And then solenoid switch contacts shouldn't see more than 300 millivolts of a voltage drop in there either. So that's a handy test to do as well. I think I have a problem somewhere within that circuit. I want to be able to do that voltage drop. Let's talk about the other measurements we can do as well. So another popular one's duty cycle. So that is a measurement of the length of time a circuit is on or off. It's expressed as a percentage. Now, most automotive components refer to that percentage as the on time. So it's either on or off. Now, depending on how that circuit is run, on time may be the high side, or it could be the low side depending on the component. So in this case, if I had to apply power to turn it on, then this would be on. But in this case, it's pulling the ground to turn it on. So that's on down here. Now notice how it's off and on the same amount of time. So that's a 50% duty cycle. If it was on 60% of the time, off 40, it's a 60% duty cycle. If it was on 20% of the time and on and off 80% of the time, that's a 20% duty cycle. Right, so that's our duty cycles and how you would measure that and what it means, what duty cycle means as that percent. Then we have dwell, most commonly used for ignition. It can be used for solenoids as well, but most often for ignition. And that's going to be the measured amount of time that the coil is charging measured in degrees of rotation. So if I have 60 degrees of dwell, it would be, here's how long it takes the crank to go 60 degrees. And that's how long I am charging that coil. So it's the on time when it pulls down to ground and say, okay, we're charging up that primary coil. We're adding voltage into this coil. And then when it releases, that's my firing line right there. Is what it would look like. Now, in this case, we're looking at a solenoid. So it's got a couple other little dips over here. That's normal for a solenoid, but a ignition pattern would look very similar. So it could be used to measure either solenoid on time or ignition, usually in ignition. And then we have frequency. So frequency is a measure of the number of times a cycle repeats. So if it's a repeating cycle, how often does it repeat? It's measured in a unit called hertz. So 1 hertz is 1 cycle per second. So it goes through that pattern 1 time a second. Some barrel sensors and some MAF sensors measure in frequency. I know there was the older GM ones, mass airflow sensors would measure in frequency. You can see it on the screen. Displayed as a histograph as well. So I can either look at the pattern or I can look at a histograph, which is what the example would be over here. If we take a look at the picture on the left, we see it takes 1 second for it to go through 1 complete cycle till it repeats again. So that in that case, this is operating at 1 hertz. Over here, from here to here is 1 second occurring, and it goes through once, twice, 3 times, 4 times. So in that case, it's operating at 4 hertz, 4 cycles per second. So being able to measure that, and we have a couple different ways we can measure that, either with the histograph or with the cursors, and we'll talk through that in a minute. And then lastly, we're going to look at pulse width. So that's a measurement of a component's on time. It's usually in milliseconds. So in this case, it's a regular standard gasoline fuel injector. Typical fuel injector on time is going to be 3 to 5 milliseconds at idle. Could be a little more, could be a little less, depending on the conditions of the vehicle. When you get to direct injection vehicles, it can be as fast as 500 microseconds, especially on piezoelectric injectors. Very, very fast. Very, very fast that those can turn on. So that's the meaning of the word pulse width. How long is this commanding this piece on? So in this case, the injector. All right, so let's go live on the tool. Look at a couple functions a little bit more in detail on what we talked about here. First off, if you have a snap-on tool with the scope in it, you're going to have many scope and meter functions. We're going to talk about a couple of them. But you also have guided component test. Now, guided component test sets it up, makes it real easy for you. It's a test database of components. But before I ID a car, because it is VIN-specific information, I also have classes available on the tool. If you're one software update behind, it'll be down here. It'll be called training and classes. They just moved it with the last update, so it's on the top now. But if I go into classes and I go to how-to, you'll notice if I need to remember stuff that I just talked about today, 10-minute electronics classes. Go in there, amperage, diode continuity, resistance, scientific notation. There's Ohms Law right there. There's voltage. Guided voltage drop test. A lot of the information I've talked about in here is in here as well. Or a lot of things that I've talked about this evening are in here as well. Different waveforms, control modules, parking assistance, airflow calculation, all sorts of information. There's 65 categories of class within the tool, all there right at your fingertips, ready for the learning at a moment's notice, because you don't even have to hook up to a car to get to that. So that's pretty handy. If you didn't know that was in there, that is a huge function inside the tool. Next thing I want to do is let's look at a little bit on the wiring diagrams here. So I'm going to load that Ford Explorer we were talking about in the slides there. I'm going to go into shop key. I'll pull up a wiring diagram. Give it a couple options, maybe. Go. All right, so this is a 2002 Explorer. We got almost 1 million repair orders available on this book. DPFE sensor. Differential pressure feedback EGR sensor. So let's say we're going to replace it. Wow, 18,000 times that's been replaced. According to that. A lot of TSBs on there too, apparently. But I want to go down here and look at my wiring guide. That's what we're talking. We could go to component operation, component connectors, things like that. I just want to look at the wiring diagram for now. And here we are on our page for the wiring diagram. Now, a couple improvements have been made. If Shopkey or Mitchell is your thing and you've tried it, want to use it or have it, couple nice improvements have been. So first off, you notice I'm on page 2 of 4. That means there's a 4-page wiring diagram, and I'm on page 2. Now, why am I on page 2? If I click to open, we will see that that's where the DPFE sensor is. So it's right down here. So there's my DPFE sensor. And it is supposed to highlight automatically, but I guess it didn't want to do that. That's okay. So there's my DPFE sensor down here. If you highlight the wires, you can dim the other wires, make it easier to see. Let's slide this up a little bit so we can get a better, closer look. I'll maybe zoom out one more. All right, so we see on this diagram, you have the DPFE sensor, and we have this 5.0 reference, and we also have the throttle position sensor, and we also have whatever this is, number 28, and whatever's on number 38. So if I go across, let me go across these. What's going on? My wiring diagrams are messy. Okay, so I guess we'll go over here. It's supposed to be able to go across. Stand by. It's not working the way I thought it was going to today. We did have some system hiccups the other day, so maybe that's why. We'll just go into here instead. There we go. We can do the same thing going this way. Oh, there it is down here. I was on the wrong page. All right, so there's my DPFE sensor right. There's my DPFE sensor right. So we can see how it shares in common with these others. So there's a different breakout right there on this particular. We can see how it goes to this. So we have this splice. Comes out of the engine. That's 5.0 reference, says volt VREF. So that goes down to my bottom of the screen here. So that's my throttle position sensor, my differential pressure sensor. Let's see, we got a couple more over on this side. And you'll see that those wires also split off. Kind of comes down here as a dotted line of my oxygen sensor. And then it loops back around and goes back to the PCM as well. So a lot of these things are tied together on this vehicle. So if I have that situation where a 5.0 reference is kind of tied together, you got to make sure, is it before the break? Is it after the break? Where's the problem lie in that particular instance? All right, so that's wiring diagrams real quick. Let's go into our meter and talk about a couple different meters and scope functions that we can use in here as well. But first off, I'm going to go just into the basic digital multi. And I'm going to read volts. Actually, I'm going to back up here once so I can actually show you what we can measure. So you measure volts DC on an average, DC RMS, which is root mean square, which is going to be the constant averaged out. Ohms, diode continuity, low amps, 20 amp scale, 40 amp scale, and 60 amp scale. So in this case, we're just going to stick to volts tonight. So we see just a digital reading. Right, so I'm seeing about 3.8 volts to what I'm connected to, roughly 3.78, 3.82, somewhere in that range. I'm seeing that voltage there. Now, I'm going to show you the difference between these meters. I'm not going to change what I'm connected to and see if we can see the difference. So in this case, 3.8 volts. If I back up, I'm going to go to my graphing meter now. So the graphing meter takes the voltmeter and graphs it over a period of time. You see, we have a 4-channel graphing meter, so we can graph 4 things at once. Volts, DC and AC, frequency, pulse width, injector pulse width, vacuum, dwell, low amps, duty cycle, pressure, and ohms in there. So we can graph ohms. I know that was out of the tool for a little while. It came back, so we can graph 4 things at ohms if we want. Volts DC, though, and that looks a little bit different, doesn't it? So why was I seeing 3.8 volts? Because what that meter is going to do is the meter is going to take a sample of the signal. It's going to average it out. So in this case, this signal is on longer than it's off. Remember, we talked about duty cycle. So this signal's on longer than it's off. So the average between 5 volts and down is around about 3.8 volts in this case. So it's on longer than it's off. So when it averages it out, what the signal's flowing, it ends up being 3.8 volts. So you can't always rely on a digital meter either, digital multimeter, because like I said, it's an average. So it doesn't always react fast enough. So a graphing meter is better. So we can see that it is an up and down volt. If I back up and go to my scope and go into volts, we can see that, well, it looks like it's going up and down as a square. So let me go in here, get rid of some of these here. Actually, went on a 4-channel scope before. So it's easier. We can see we got a square wave there. We're on a 5 millisecond time base. So I want to change that a little bit. Let's go to like 100. That's okay. Let's go to 500. There we go. So 500, now we can see the signal in closer detail. We can see the on versus off time up there. Let me pull down my trigger as well. So you can see my on time versus the off time. That would be your pulse width. No, not your pulse width. No, your I just lost it there. So your on time versus your off time in a percentage. So there's a couple other things we can do here as well. If we wanted to check, say, the frequency, there's a couple different ways we can do that. So remember how I said some signals go in frequency. So we'll put on our cursors here and we're going to measure frequency. So I need to, in case, one time through this pattern on the screen. Now I can't really measure it until I stop the recording. So stop it. And it jumped a little bit, but that's okay. We'll move it on. So as we can see, this is a repeating pattern. I need to pull up my measurements here. It's a repeating pattern. So that is one time through the pattern, and then it starts over again, right? So that's one time through. So we have a frequency measurement down here on the bottom right-hand corner. I get 13.37 hertz if I do this manual measurement. So we can also go back and we can go into the graphing meter and graph frequency as well. So we can go into frequency here. And we should be able to see now this is a little bit high, but it's showing me 13.4, 13.3 at a minimum, 13.5 at a maximum. If I wanted to modify this a little bit, bring my scale down a little bit, because I know it's low, down to like a 50 hertz scale. We can see it's a little bit below 15 there, wavering a little bit. I want to change my frequency up or down. I'm going to change a different button. There we go. Bring my frequency up. You'll see it goes up. I got around about 35 hertz now. Come down here around about 5 hertz. So we can graph frequency and measure frequency this way as well. So we can either calculate it manually with the cursors, or we can do it this way with the graphing meter. And that's duty cycle was the word that I was looking for. It's on versus off. So we can measure duty cycles, a whole lot of things that we can measure in here. And it's really up to the manufacturer specs as to what they're measuring in. This thing transmits in frequency. This thing transmits in AC. This one transmits in DC. So you really need to check the manufacturer specifications for what it's supposed to be. But understanding at least the basics can help you understand a little bit more about what you're trying to test with that. And with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.